you can, to actually subtract the energy from the channel, what you have to do, you have to estimate the phase of your signal at the receiver. And this phase will change if you misestimated the distance, if there are reflections, if there are, it's practically almost impossible to cancel out, right? And the wider your channel that you work on, obviously the task is more difficult for the attacker. So what we have here is a primitive which allows us to protect the integrity of our message on the channel. So whatever the base station sends, the attacker cannot he can modify it, but not without the receiver noticing the modification. And we didn't use any keys. We just used publicly available channels. We just said, well, on this channel, in this space, there is a transmitter which is trusted. There might be 10 other untrusted transmitters around. You don't care. So in order to show how this can be done, well, what you can do is if you have a 1 and if you want to send a truly random signal, you can simply change the phase, and then you can compute what is the probability that the attacker can attenuate your signal within a given. So you can make this as fine-grained as you want, depending on your system, on your frequencies, and so on. So there are some things that can be tested here, how an attacker could do early detection and then try to invert, but these are very, very sophisticated. These might turn out to be extremely difficult tasks to do. So, we essentially also came up with, if your navigation messages are not of a fixed length, if you want to send some other information, well, you can also use some, we call them I-delimiters, which are some delimiters that you use for synchronization, which have a specific property that they can never be turned into a part of the message, and therefore you can use them as delimiters for your messages, and using this you can recover your signals between the delimiters. So this is kind of a building block that we proposed in 2006 that we used. We kind of went in with an idea of how can we do broadcast authentication or integrity verification without using any signatures or any keys, MACs, distribution, or whatever. The only public information we need are the channels. So this gives you a very nice property, meaning that if you know that there is an access point here on campus transmitting on channel 5 all the time, if it transmits, for example, a public key of a network, then you will always, whenever you come to Purdue, you turn on your computer, you switch to channel 5, you will either receive a legitimate public key or junk. And you can count on that. So this was the idea that we used here. But now, how can this be used for secure navigation? Well, the answer is simple. It's almost straightforward. What we can do is we can now take any navigation message, either in a GPS-like system, which is based on time of arrival, and send it using this scheme, using integrity coding. Well, what happens then? Or we can use a beacon-based scheme. Well, what happens here? Well, you essentially prevented any time shifts of the navigation messages, because in order for the attacker to simply take a message that appeared in the past and replay it at another time, since you are constantly transmitting, they will mutually add up, and the integrity of the messages will be violated, and as a receiver you will notice that something is wrong. So you again have this integrity property, and the attacker cannot shift your messages in time. You can do it either with beacon-based or with time of arrival or time difference of arrival-based schemes. Well, given that time of arrival and time difference of arrival schemes are a bit involved to implement, we did an implementation using 802.11. So on one side we had a regular laptop with a wireless card, and we had a receiver which was a software radio, just in order to be able to observe in a bit more fine-grained way what's happening on the channel. And this is what we got. At first we thought, and these were the measurements done at the ETH campus. So at first we thought, well, the noise will be so high, and then, if you have these channels, maybe it will not work out. But surprisingly, it worked like a charm. These are ones and zeros, right? And they're, as you can see, they're very easy to distinguish. Even up to 70, 90 meters, you can fairly nicely distinguish between background noise and your signal. So it only depends on how you tune your signal, your system. Obviously, if someone interferes here, he will kill your system. But well, you can do, since the beacons are being transmitted all the time, you can definitely, for occasional interference, you're pretty fine. So we ran into some issues of how to do coverage, right? If you have a wider area, and if you want to cover this wider area with some channels, then two beacons transmitting on the same channel may mutually, two base stations transmitting on the same channel will mutually interfere. So we can come up with a certain scheme that we have full coverage with 7 channels where there will be no mutual interference, or better said, it will be fairly minimal interference. These numbers give you the channels that we use from each of these base stations, and with a bit of thinking, you will end up seeing why this works out so nicely. Also, in terms of how fast can you go here, well, it really depends on your equipment. But using what we are using here with 802.11 based implementation, 500 bits per second, which is perfectly fine for a navigation signal. But then we also had, I don't know if I have the slides on that, but we had a custom built device, a custom built pair of devices doing this integrity coding and doing this navigation, and we transmitted at 20 kilobits per second. So it depends how fast you are, how narrow your signals can be, and so on. And you can play with this in terms of robustness. How narrow do you want your system to be, and so forth. You can also do various optimizations. So, for example, you can transmit only so if this is your original message, you can transmit it over a normal high bandwidth signal, a high bandwidth channel. And then you can simply transmit a digest, like a hash, of your navigation message using integrity coding. Because then you need to transmit only 160 bits, and your message can be as long as you want it to be. So, what does SecNav really give you? Well, it gives you secure broadcast localization. It also gives you secure broadcast time synchronization. I didn't go into that too much. And it can be implemented on a number of legacy systems. Also, it can equally work on time of arrival or time difference of arrival systems. We haven't implemented that yet, but we are working on that. So, and an application of this is, you can generally use it on a campus. You can use it in any confined area where you have some awareness that you are within an area of interest. That within this area there is a secure navigation system up and running, and then you can turn on your device and say, okay, now I'm here within this area. It can be a city as well if you set up such an infrastructure within that city. By the way, this requirement, if you think about it, is not that strange, because almost the same requirement holds for GPS. If there is no GPS coverage in this room, I can feed you with whatever I want, and you will pretty much buy my location. So these 3 dots there stand for more, for those who want to know more, right? We didn't stop here. This was actually just one of our latest projects. We did a lot more earlier on a slightly different problem, which is if I have a device which maybe has a correctly computed location, it knows where it is, but wants to lie. So wants to tell me that it's somewhere else. What do I do? How do I know that this guy here is that this P prime is equal to P? Maybe it's something else. Maybe it's a different location. Because an attacker might have some incentives like access control or whatever else to claim that it's somewhere else.